In the next video, we are going to see about the engineering material classification. So, as you know, there are 1,60,000 materials are available, but it is classified based on the materials and its application. So here we see six broad families of material. It has got materials, polymers, elastomers, ceramics, glass, and hybrid material shown in the figure. So hybrid, it is a combination of two or three materials. So in the hybrid materials, we have composites, which has got sandwiches, segmented structures, lattice, and foams. So under hybrids, here you can see polymers are there. Under polymers, there are different materials like polyethylene, polypropylene, polytetraethylene, polycarbonate, polystyrene, like nylons, like this different materials are there. Next, coming to the elastomers. Elastomers, it has got elastic property. It may be butyl rubber, neoprene, isoprene, all these things are the rubbers. Natural rubber, silicon, and EVA are the elastomers. So further coming to the glasses, we have got soda glass, borosilicate glass, glass and ceramics combined together, silica glass, soda glass, like this different type of glasses are there. Further coming to ceramics, there is alumina, silicon carbide, silicon nitride, zirconias, all comes under ceramic category. When you come to metals, we have cast iron, aluminum alloys, steels, copper, zinc, titanium alloys are there, which is to be considered as the metals. So like this, these are all the materials which we are having in the existing scenario based on the sequence select. So how to check the material properties of the given material? So when it comes to count the material properties, each material can be thought of as having a set of attributes of properties. They combine their characterize a given material is its property profile. Property profiles are assembled by systematic testing. So mechanical properties, you are going to check out with the tensile strength of the material. You are going to count Young's modulus, bulk modulus, shear modulus, material subjected to tensile or compressive loadings. So based on that, you'll be able to get the stress strain, and if you consider the slope of the graph, then you'll be able to compute the Young's modulus. So here we can see the ductile, when we can check the material property at how it behaves when the stress versus strain is plotted. So you can find out the Young's modulus. You can find out after what load the material will be elastic, or it is going to take ultimate load, or when it is going to fail. So accurate modulus can be measured by using the Poisson's ratio, that is the strain in one direction by strain in another direction. So isotropic material, we can calculate the Young's modulus, bulk modulus, and the shear modulus by the equations shown here. So by this you'll be able to know the strength of the material. So like this we can extend to different material. If we can consider a polymer material, and you can check how it behaves, whether it's a ductile polymer, brittle polymer, or you'll be able to know the plasticity, and you'll be able to know when you're going to do the cold drawing operation and what range it will be in the viscous range. So based on the temperature, when it is plotted with respect to stress and strain, you'll be able to compute the graph. So here you can see the variation based on the load what you had initially. Up to certain point it will be brittle, up to certain point it will be elastic. So like this we can combine. So when we take ceramic material, when the stress strain curve, so it is a brittle material. So but you can see that it can take load up to certain point. After that it will keep on failing further. We cannot expect the things to go. But the compressive strength of the composite material, it is 10 to 15 times greater than the tensile strength. So that is the advantage. But it is brittle, means if you add load heavily at the certain point, the specimen may break or the material may break. So modulus of rupture, which is going to happen on the surface, it is equal to or slightly larger than the failure stress and tension. So force versus deflection, if you count, it is it is the modulus of rupture which is going to MOR, it is going to happen. How to check out means with the equation mentioned here, you'll be able to calculate. So you can take this specimen as per ASTM sign and apply the force at the center. Then we can see the modulus of rupture, it is going to happen for the material. So fatigue curve, it is counted for number of cycles what all it happens. So every material it is going to observe fatigue when we go with excess loading on the material. So material how it behaves. So up to certain load it will be able to tolerate and it is going to come back to the initial shape. So if we increase the load further, the performance of the material or the product it is going to fail. So hardness of the material is measured when we plot load versus area. So you can use any hardness test. It may be Vibrinel's hardness test or Vickers hardness test. So based on the material, we'll be able to check. So Vickers and the Rockwell's and Reynolds, you can see I got a specific indenter based on the shape. So if we apply load on the indenter, you'll be able to get different shapes. So the correspondingly, you'll be able to observe the reading on the surface of the specimen. You'll be able to get the output. So when we measure with going with the fracture toughness of the material here, initially you have to create the wedge width of 2C and apply the load on both the sides of the slots provided there. So here you can see the fracture toughness K1C, it is calculated by using this equation. So here if you apply load on this, it is going to crack is going to initiate from this region where we have developed the slot and it is going to move. So where our loss of material and surface slides against each other is a multi-body problem. So now here we'll be able to know the toughness of the material by applying the loads with the slots indicated over here. So here there are two slots where you'll be able to check out the material loss from one surface per unit area slit, which is known as the wear rate.